Okay, time to get started. Real quick before we get into the math. Reminder, homework is due on Fridays. It's due at the start of class up here at the front. Stapler should be operational. Oh, I owe somebody some staples. Somebody filled the stapler for me, and I forgot who it was. I'll try to remember to bring staples at some point. The other thing related to homework, I know I haven't given you any homeworks back yet, and that's because we are, in some sense of the word, still without a grader for the course. But the grader, I'm told that it should be okay, that we should be okay with the grader sometime in the next few days. That's going to be 3 homework sets that y'all have already turned in. They will get graded. They still will count as part of your grade. It's just there's going to be a delay in getting them back to you. So apologies for that delay. Yes.
Will you know exactly tell us what you did in this?
I very much hope so. That will be a goal. Yeah. Right. Okay. Cool. All right. So here's where we were last time. Here's the new topic after the stuff that we covered last time. We're going to talk about limits. Y'all probably remember limits from single variable calculus. By the way, I'll point out that how limits are treated in high school calculus courses very often leaves a little something to be desired. I want to encourage everybody to make sure that you're actually pretty strong with limits. Now, I recognize that most high school courses do not cover the epsilon delta definition of a limit, and that's okay. We're going to stop short of expecting that you're strong with that idea. Nevertheless, it doesn't hurt. Just a cultural point. I'll note that until the epsilon delta definition of a limit was actually really fully worked out, there were, historically speaking, complaints about the very concept of calculus. And you think about it, there's something kind of fishy about this idea of, I'm going to treat something like it's infinitely small. What does that mean? What is infinitely small but not zero? Is that a thing, or is that made up garbage? Kind of sounds like made up garbage. Anyway, so that's fully resolved with the epsilon delta definition. Arguably, it's a point of formality, but given how central limits are to all of calculus, right? Derivatives are defined with limits. Integrals are defined with limits. It's kind of a big deal. Right? So it's as a cultural point, if nothing else, it's important. Anyway, make sure that you're good with limits, how to compute limits. And I'm going to make a couple of comments as we go along today about single variable limits. But I'm also going to point out, while we're here on this topic of single variable limits, I have a playlist on my YouTube channel called Miscellaneous Topics. In that playlist, I have put some little short videos, less than half an hour, I think, mostly, if not all, of videos on topics that I wish my students in one course or another were stronger on than they perhaps are. And one of the presentations and one of the recordings in that playlist called Miscellaneous Topics is on limits. So if you're not 100% sure, if you're maybe a little, I kind of get it, but I'm not sure I'm right, right about limits, watch that video, please. It'd be very, very helpful. Okay. All right. So here's a broad brushstroke idea of single variable limits. If you're going to say that a limit exists, then the limit as you approach from the left and the limit as you approach from the right, hope you all remember these two things defined differently. Okay. These two things have to equal to each other. If these two things do not equal, or if either one of them fails to exist, then the limit does not exist, right? So limit means that both of these things exist and are equal. Okay. All right. So I'm just going to, again, avoiding the epsilon delta definition and rigor and formalities that are not really quite appropriate for Math 212. I'm going to pretty much rip off that idea for defining a multivariable limit. So if you want to define a limit as you approach a point in the domain of a multivariable function, so now instead of some value on the x-axis, we're talking about a point in a, let's say, a two-dimensional domain. Right? You just have to consider all of the limits as you approach from different directions. It's just that now, instead of there being only two directions, right, there's really just not that much room to move around in a single variable domain. You can come from the left, you can come from the right. There's no other options. It's very claustrophobic, right? But look at all the room that we have to move around in a multivariable domain. You could approach that point from this direction, or you could approach from that direction, or you could approach from along a curve, or you could approach along some sort of weird spiral. There's lots of different ways that you can approach that point. And if we're going to say, now this is just a sort of intuitive appeal, surely if we want to say that a limit exists as you approach that purple point, surely along all of these paths, we must have to get the same answer along all these paths. I mean, if there were two of these paths where you get different answers, right, something like that happening, right, it's a great big gap, right? Something is terribly, terribly wrong with this function, and we would not want to say that, oh yeah, we can talk about the limit. Okay. So that's the big idea. Now, before we get to in practice, I do want to point out something about this picture that confuses a lot of students. This is a picture of the domain of the function, right? So you should remind yourself that the function is like this, and there's also a target over here that is a totally different world, right? In other words, this picture that I'm looking at in yellow, this is not a picture of the graph of f. Not at all. This is a picture of the domain of f. Inside of the domain, what are we doing? I don't really want to draw graphs for reasons that I'll show momentarily. And you'll notice, by the way, that's why I drew over here a picture of only the domain. Right? And the actual function, well, yeah, if we have some single variable function, it's got output values, way over here. And we were only looking at pictures of the input values. Okay, now, if you say, okay, well, yeah, but all my intuition for limits comes from a Calc 1 class where, of course, we were drawing graphs constantly. So what does this all look like in the graph context? Well, here's a picture in the graph context, right? Here's our domain, if you will, at least as it's sort of embedded in R2. And then here's the target, and we draw graphs as usual as these curves that kind of do like that. And this is, you can have some sense of intuition of what limit means, because look, as you approach along these different paths, keep in mind as you approach maybe that way or this way, that on the graph I need the values to be kind of approaching some agreed upon value. And analogously, in a multivariable context, what we're kind of talking about is there's your domain, now a two-dimensional domain instead of a one-dimensional domain. Right? Still, we're looking at real valued outputs, right? So real valued, how does the target kind of show up in this R3? It's sort of the z-axis. And we are talking about, again, the graph. The graph is, over here the graph is a curve. Over here the graph is not a curve. The graph is a surface. And we're contemplating, as we approach along different directions in the domain, we're talking about how then correspondingly in the graph, the values of the function approach, hopefully, some value, some shared agreed upon value in the outputs. All right, so now this is my case then for why I don't want to draw graph pictures. That's a hard picture to draw, right? And let me complain. I already complained about this, but if you look at what's lacking in this picture, what's lacking is in the area where I really need to see what's going on. Right, I need to see I don't really care about what's going on over here or over there or over here. What's really going on as I approach, in this point on the domain, as I get closer and closer, what's really going on there, and I didn't draw anything. Right? I'm kind of, psychologically, I'm trying to trick you into thinking that I drew something in this vicinity, but check the pixels, right? This is all white in there. I didn't draw squat. So it's really hard to actually draw a useful picture with a pencil, right, of a graph that will give you intuition for what a multivariable limit sort of looks like in the graph setting. Right? And that's just a big difference between how pencils work for multivariable calculus versus how pencils work for single variable calculus. In single variable calculus, the graph is a curve. Pencils are great for drawing curves. I can actually literally draw the entire curve. Couldn't ask for a better type of a picture there. Right, so you got to kind of mindset, sort of, jettison this idea of I'm going to think about limits in terms of what the graph looks like, because it's just not going to work. Okay, so instead, we're going to look in the domain. Think only in the domain. We're looking at, when I draw pictures, I'm going to tend to draw just the domain because that's all I can really visualize anyway, and use the domain simply as a way, forget about the rest of what's going on over there. We're going to draw the domain just as a way of distinguishing all the different paths along which I'm approaching the point in question. Okay, all right, so let's do it. Let's get our hands dirty. Let's consider this multivariable limit here. Now, notice we have a function. Right, this is a function from R2 to R1. Right, so in my domain here is two-dimensional. I have 2 different variables for that function. We're considering the limit as my vector position x in the domain approaches the vector 0, namely the origin, also in the domain. This is all happening in the domain, right? So we'll draw pictures kind of like this. Here in this domain, the xy plane, we're going to draw pictures of all the different ways that we're going to approach the origin. Okay. All right. So now I'm going to take a very unorganized approach to checking all the paths toward the origin. Asterisk. I'm going to come back and comment on that in a couple of minutes. But let's start, with an easy choice for a first path. Let's approach the origin along the positive part of the x-axis and just head straight for the origin, nice and boring. Right? So along the x-axis, and algebraically, how do we write down approaching along the x-axis? Well, along the x-axis, notice that y is equal to 0, right? And x, the x-coordinate, is approaching 0. And I want to distinguish now, heads up, be careful, this is just the variable x. That's approaching the number 0. That's not to be conflated with the vector position, x vector, x comma y, approaching the vector, 0 vector. Okay. All right. So, how am I gonna along this path? How am I gonna resolve what's happening to that limit? And it's good news. It's very plug and chug. So I am literally going to take what I've got there. I'm gonna stick it in. I'm going to see what that turns into. It's very plug and chug. So specifically, y is equal to 0. So let's stick that right in there. Y is equal to 0. Y is equal to 0. Note thus this. Right? The scalar coordinate x is approaching 0. That's what we're doing there. So x approaches 0. And we've got ourselves a single variable limit to address, right? If I want to know what's happening along that curve approaching the origin, this Math 111L problem answers that question. Before we go on, is everybody on board with that? And you see now, by the way, why single variable limits are important, right? Single variable limits are how we are going to deal with multivariable limits one path at a time. Okay. Right, okay, so heads up, landmine. Lots of students step on the following landmine, which is to look at this formula right here and say, oh, well, it's 0 over 0, right? Because look, 0 is both the top and the bottom are approaching 0. So this is isn't this like an indeterminate form or something? And Totally not. We certainly don't have to take that point of view. It's much easier than that. Keep in mind, now here's a common misconception, common misunderstanding for undergrads coming from high school backgrounds. When you say x is approaching 0, students kind of want to think in terms of that, meaning that x should be thought of as 0. And in fact, it's exactly the opposite. Saying x approaches 0, the whole point of saying that we're approaching 0 is because we don't want to deal with what's happening when x equals 0. So x approaches 0 means that you get to assume that x is never 0. Again, that's kind of the whole point of limits, right? So x is explicitly not 0. So now, the fact that this is not 0, and I encourage you in your mind to every time you see this, every time you see x approaches 0 in your mind, you should be thinking that means x not equal to 0. Okay, well, what that means is we have, pretty straight up 0. Now that is actual 0 in the numerator because, again, y is 0. Here, I should have done, I labeled that wrong. Y is actual 0, not approaching 0, not approximately 0, actual 0. Okay? So the numerator is 0. The denominator, on the other hand, is x squared, where x is not 0. I have actually here 0 divided by not 0, and that is, there's nothing subtle about that. That's just flat 0. It's not an indeterminate form, or we have to be delicate and properties of limits or something like that. No, it's just plain old 0. Is everybody good with that? Does everybody catch the point here? If you're a little shaky on this, again, I can't turn this into a Calc 1, single variable limits refresher, but make sure that you're really comfortable with those observations and the immediate resolution of this single variable limit as being just plain old 0. Okay. All right, so we have a partial answer. We've decided that as we approach along that curve, the limit is 0. Now, that doesn't really tell us much of anything about the original limit. We're responsible, don't forget, for checking all possible paths, not even just the straight lines. We're also responsible for all the spirals and all of the, parabolas and, oh my gosh, all the different paths that approach the origin. We have now checked one. Right? Okay, let me try to be a little bit more efficient. Instead of just checking the paths one at a time, we don't have that kind of time. It's not realistic. Next, I want to talk about, let's consider not just a straight line approaching the origin, but notice since I didn't indicate what M is, this is actually all straight lines approaching the origin, with the exception of the y-axis, of course, where there is no M that makes it on the y-axis. But this is the vast majority of straight lines. Okay, let's see what happens. Again, it's very pluggy-chuggy. If y is equal to mx, just plug that right on in there. See what happens. Y equals mx. Notice that y, that is now mx, when you plug that in, you get this single variable limit. And again, single variable limit, follow the rules, play the game, compute that single variable limit. And in this case, we get that value. Now, the careful among you might be a little uncomfortable with this whole thing. Hey, wait a minute. Didn't I just cancel a bunch of x squareds? And isn't x like 0 or something? Are you allowed to cancel 0 over 0? Isn't there a rule against that? And I remind you, very important distinction, the whole point of this limit is that x is never 0. We can make this cancellation not despite x being sort of 0, but we can make this cancellation because x is never 0. Yeah? Everybody on board? Okay. So, yeah, there you go. Now, what does this prove? for us. And it actually proved something really nice. We have now checked along two different paths. Along this path, we got 0. Along all of these paths, we got something else. Very importantly, these are not always the same. I mean, this silly point, but there exists at least one value of m where that thing down there is not 0. So I've got two different values along two different paths toward the origin. I've got two different values of the limit. It's got a great big gap. In at least some sense, this is kind of like a jump discontinuity. The limit does not exist. And so, drop the pencil, walk away, right? This limit does not exist. Is everybody on board? Okay. Yep.
What would happen if those were the same?
Yeah, that's right. We're going to get to that in a couple of minutes. Yeah, that's a great question, and I'm going to spend some time on that coming up real soon. Yeah. Okay, so in fact, let me point out an even slicker way to solve this problem. I deliberately did not do this the slick way off the bat, but I think it's nice to start with just a single path, just to kind of get the ball rolling. Let's keep it easy for that first one. But in fact, I didn't even really need this first step, because notice it's that is one of these, m equals 0. I don't need to do it separately. And even if it wasn't, this thing right here, I don't need to point out that it's not 0. All I need is to point out that it's not always the same. Just do this one calculation and then plug in two different values of m. Let's see, when m is equal to 1, you get a half. When m is equal to 2, you get not a half. And so again, two different values along different paths, and who cares? Drop the pencil, walk away. This limit does not exist. Right? So I encourage you never to just actually do a single path. Why would you do that? Just do categories, large categories of paths like this. Yep.
Is that also y equals mx?
Yeah. That was part of my point. Is that along the x-axis is the m equals 0 version of that. Totally. Yeah. Okay. So let's look at this one here. Now again, function of two variables. We're going to think about in the domain what happens as you approach along different curves. Let's start again with all of the straight lines. Let's plug in. Let's see what we get. So y equals mx. And algebraically, y equals mx. These y's turn into mx there. Right? Move things around, cancel your common factors of x. Again, you should always, whenever you cancel, you should always kind of pause and hesitate and say, oh gosh, am I allowed to do that? Can I cancel? You're not supposed to cancel zeros. Might the thing that I'm canceling possibly be 0? It's not in this case. X is approaching 0. That means x is never 0. And so you're allowed to cancel it all you want. You cancel those common factors of x, thus turning this into this. Now we have another easy Calc 1 limit, because as x approaches 0, that thing right there is a great big constant. We are looking at the limit of x times a constant, and the limit of x times a constant is, it's just that constant, right? So this limit, the limit of x times a constant is 0, because x is approaching 0 and the constant can't overcome that. Sorry, I misspoke. Everybody on board? Okay. What did we prove from this? What did we conclude? We've checked all the different directions. Does that mean that the limit is equal to 0? Because from every direction we always get 0? Actually, sadly, no. This does not tell us anything. All this means is we've checked we've checked some of the different ways that we could approach the origin. We don't get any contradictions among those paths. That doesn't mean other paths won't give us contradictions. What if we approach along a parabolic path and all of a sudden we get 2? right? Then the limit couldn't possibly exist. So this is one of the unfortunate features of viewing multivariable limits with single variable, one path at a time considerations, and that is it can never really prove that a limit exists. You can never check all the paths, even if you're doing huge categories all at once. So we have to keep going and hope, fingers crossed, that we get a contradiction. Here we get no contradiction, so we learn nothing. So now let's check along parabolic paths. These are not straight lines. We haven't checked these yet. Who knows? Maybe something weird would if you kind of bend it into the origin. Maybe somehow that'll change something. It's hard to figure, but so algebraically, again, stick in mx squared where the y's used to be. Play the cancellation game with the x's. You get down to this. Here I'm going to cite a different property of limits. Now this is another thing that students are a little shaky on. Here we're looking at the limit of a fraction, and I've rewritten it as a fraction of two limits. Can you do that? Got to be careful. You can do this sometimes, but in order for this calculation to be true, you need two things. You need for both of these limits to exist, and you need to know that that denominator limit is not zero. Right? So if you have otherwise you may have what's called a 0 over 0 type indeterminate form, and you cannot draw conclusions about it just by naively assuming that limits of fractions are fractions of limits. It's just not always true. They're pretty easy counterexamples to show us this false. So, good news. This limit does exist. Easily seen that this single variable limit's 0. Okay. This limit also exists. Easily seen that this limit is 1, which is not 0. And as a result of that, and only after checking that, can I actually say, yes, that's actually a true statement. Right, so again, be real careful with this. Right, be super careful. Lots of students are accustomed to, moving limits around kind of willy-nilly, like they're just part of the algebra, and you can just kind of toss them around in whatever way seems intuitive. Not so. So be careful. Again, if you're a little shaky on any of this, office hours would be a pretty good time to come straighten this out. And you can also look at that talk I gave on limits. Okay, so again with the 0. Now, what do we conclude from this? So we tried along all of these paths, we got 0. We tried along all of those paths, we again got 0. What can we conclude from the fact that we've tried now not only infinitely many, but in some sense double infinity many paths toward the origin? We got 0 in all cases. We have found nothing resembling discontinuity that we can detect from anything we've looked at so far, and that means very little. We cannot draw any conclusions from this. Again, the lack of your experience with contradictions doesn't mean that there aren't contradictions out there somewhere. So, this approach, very important point. Again, a lot of students don't digest this. Checking different paths can absolutely show that limits don't exist. It can never show that limits do exist. Yeah?
So are we never going to have a problem where we're finding the limit of more than just 2 dimensions and the limit will exist?
So I don't want to generalize that. I'm just going to say what I've shown you so far does not allow us to address that. That's right. Yeah. So there are a couple other techniques that I'm going to show you. Yeah. And these other techniques are different and a little bit more sophisticated than this. Yeah.
So I remember we can use the Taylor expression to expand a polynomial so that it will represent any of the problem.
In this class we don't have any indication yet of Taylor series for a multivariable function. Yeah, right. And in fact, we're not going to write that. I'm going to make a vague reference to it. There is such a thing, but that's a shooting a mouse with an elephant gun type situation. It's actually pretty heavy material to even talk about Taylor series for multivariable functions. Yeah. we're going to have better ways. Yeah. Okay. All right. So, by the way, just heads up. Don't say I didn't warn you, right? If you write this, get 0, and declare that therefore the limit's equal to 0, you'll get very few points on the question. Because, yeah, you did do something that's relevant to the problem, but your conclusion is fundamentally flawed, right? It's not only a wrong answer, but it's dramatically bad reasoning. Completely illegitimate reasoning. So, heads up. Likewise, if you do, this and that, and then declare victory, therefore the limit's equal to 0. Again, very few points, because it's dramatically bad reasoning. Okay. All right, now, if you're rolling your eyes and saying, come on, how could this come on, look, we've checked so many paths. We got 0. I mean, really, do we have to keep going? What could possibly happen here? How could there be a function that has all of these zeros and yet somehow the limit fails to exist? Come on, right? Well, consider this example. Now, it's a little bit weird, I'll grant you. Look at that, there's a 7th power here, and that's kind of, all right, that's a weird example. Right, yeah, okay. But it's not the weirdest thing ever. It's still just a ratio of 2 polynomials. It's not that creepy. Right? And weirdly, if you check along all straight lines, you get 0. You check along all parabolas, you get 0, and roll your eyes all you want, and try to convince yourself that, come on, that's got to mean something. But if you check along the cubic paths, and if you go through carefully, you get not 0. And we've got ourselves contradiction. We've got ourselves again, some sort of a kind of a jump discontinuity sort of kind of thing. And this limit does not exist. So if you declare a limit is equal to 0, when this happens, I mean, again, it's just complete nonsense. Yep.
Is there any way to visualize?
This is a weird one. It's a very hard one to draw a picture of. I think there's a picture in the book. But it uses computer graphics and shading that I couldn't begin to do with a stylus, right? And there's kind of an example sort of analogous to this. It's a little bit easier to visualize that I can make an ad hoc construction paper model of in office hours that I can show you if you come on by. But it's pretty weird. Yeah, it's hard to. There are no analogs of this in single variable calculus. This is part of the ways in which multivariable calculus is in some ways really different than single variable calculus at a very deep and fundamental level. Yeah, totally. Okay, so heads up. Okay, so somebody's already complained. Well, we can't check all the paths. That's not feasible. So, can we ever show a limit actually exists? And there are various techniques on this. By the way, what I'm going to show you in this course will not be exhaustive. I'm not going to show you how to deal with and consider every possible limit on conceivable. Correspondingly, good news on the exams. You will not be expected to deal with every possible, right? So every limit that I ask you to address on the exam is going to be a limit that can be addressed satisfactorily by techniques that you will have seen in this course. So how could we ever show that a limit exists? Here's one example. This is a really clever idea, and that is to convert a multivariable limit into polar coordinates. I hope some of y'all have probably seen polar coordinates before. The idea is that given a point, let me do it like this. Given a point, rectangular coordinates x and y could be replaced with, converted to what we're going to call polar coordinates r and theta, measured as that angle and that. I'm going to, just to get the ball rolling, let me say distance. I don't mean distance. R doesn't have to be positive. R could be negative. But, once you define a direction, pretend like you can then talk about a coordinate in that direction and it could go the other way. R would be negative. That'd be fine. With that being set up, we can define these to be the polar coordinates of a point. And if you get a problem that comes to you in rectangular coordinates, you can just say, you know what, I'm going to look at this in polar coordinates, and you can make the following really convenient argument. Here we go. No matter what path you have that approaches the origin, right, if the x vector approaches the origin, right, if your x and y approaches the origin, notice that means that r and theta, the point approaching the origin in the language of r and theta is equivalent to just saying just the coordinate r approaches 0. Right, so it's a neat fact. This is an if and only if. So I can understand this multivariable limit with this single variable limit. And that's really convenient, right? And that's a peculiarity of polar coordinates. Furthermore, it's a peculiarity of considering limits approaching the origin. If you're approaching any other point, there's lots of different points that have the same r value, and you just can't make such an equivalence. It doesn't work, right? But if you're approaching the origin, this is a way to turn a multivariable limit into a single variable limit. And so, for example, let's consider this one again. You may recall that we kind of crashed and burned on this example. Previously, we checked all the straight lines. We checked all the, what I'll call vertical parabolas approaching the origin. We kept getting the same answer. We got 0 in all cases, and no contradictions, but no conclusions either. We had this kind of like stalemate with this problem. Right? Well, we're going to now solve this problem. All I'm going to do is convert into polar coordinates. Notice we get a single variable limit, r approaches 0. Converting, x is r cosine theta. Likewise, y is r sine theta. Conveniently, x squared plus y squared is r squared. Something really nice has happened. Our denominator has simplified really nicely. Right, 2 terms have now canceled to become just sort of one term in a way. And then I can cancel the r's. Right, so there's 3 factors of r in that first term. There's 3 factors of r in that second term. Those 3 cancel with these 2, and I'm left with just a single factor of r. Now I don't have a fraction anymore. That's a big win. Right? And so this problem is simplified in some really nice ways. We've gotten rid of the fraction. We've gotten rid of the multivariable limit. We have now just a single variable limit. Polar coordinates has made this problem a lot nicer. Is everybody on board? You ready to follow me? Okay. Well, before we kill this problem, let me just remind you again, it's got to be the origin. This only works if you're approaching the origin. That's any other point other than the origin. This simply doesn't work. You just can't. Yeah. Okay, so what do we do about this expression? Now, we have a problem with this expression. With this expression, I know that r is approaching 0, so I understand what's happening to that factor. But if r is approaching 0, what does that mean about theta? And therefore, what does that mean about this other factor? And the bad news, I am sorry to report, is that knowing what r is doing doesn't tell you anything about what theta is doing. Theta could be wiggling around wildly in who knows what way. Theta could be all over the place. For example, look back at this picture. Right? You look at this path. Theta is constant at some value. But here's another path with r approaching 0. Theta is different. Here, theta is increasing toward infinity. Here, theta is vibrating back and forth. We have no control over what theta is doing. And so we've got to be careful. You can't just look at an expression and say, this part's approaching 0, so come on, what could possibly happen? You got to recognize that even though one factor is approaching 0, this factor here How do you know that's not running off toward infinity? Theta could be doing anything. So the nice, you can see I already have it written here. The nice point here is that theta might be doing wild and crazy things, but cosine theta always between -1 and 1. Sine theta is always between -1 and 1. And so this expression, I don't know exactly what the upper bound is, but it's obviously never bigger than 2. It's never less than -2. Right? So we have something bounded that we're multiplying by something that's approaching 0, and y'all may recall there's a theorem called the sandwich theorem from single variable calculus, right? If you have something that's bounded multiplying by something that's approaching 0, this is morally equivalent to the sandwich theorem. This limit then is 0. This calculation applies to all paths. We have successfully checked all paths because every possible path toward the origin has r approaching 0. And therefore this does tell us that the actual multivariable limit is 0. And we've computed a limit. Is everybody on board? See, everybody, this is a clever move, isn't it? Yeah. Questions? Everybody happy? Okay. All right. Okay, here's another quick example. Let's try to take this same approach to that question. And now I skipped a bunch of algebra here, but you can plug in x equals r cosine theta, y equals r sine theta, plug in, convert, cancel common factors of r, and what you get is this. And now can I take the same approach here? And say, oh, well, come on, we've got to be able to draw some conclusion here. And no, we can't, because we have something that's bounded, and it's nice that this is bounded, but it's not being multiplied by anything. Right? So this is just bounded but uncontrolled, and we have no idea what that's approaching. In fact, let me say that differently. That could be approaching lots of different things. In fact, along this path, we're going to get some value. And along this different path, we're going to get what is pretty easily seen to be a different value. These are approaching for different values of theta. You plug in 2 different values of theta, you're probably going to get 2 different values of that expression. Swing and a miss, contradiction, limit does not exist. Yes?
Did we not find a contradiction for the one that we just said was 0?
No. For this one here, so you're referring to when we considered it previously. What we found when we considered this previously was that it approaches 0 along the straight lines, along parabolas. It also approaches 0, and we just kind of threw up our hands and said, okay, well, I don't know where to go from here.
Did we not do the y equals
the cubics?
The cubics.
That was for this different. This is a totally different limit. Yeah. Okay. Yeah. No worries. Okay. All right. Okay. So let's see how we're doing on time. Oh, we're tight. So continuity. I hope y'all remember continuity from single variable calculus. It's a very important idea. Continuity. A lot of theorems that apply in single variable calculus apply only if a function is continuous. And if a function is not, and by the way, there are plenty of functions out there that are not continuous. And the theorems that you would like to plug into are not, they're not wrong just in some sort of subtle, mathematicians are uptight kind of way. They're dramatically faceplant wrong, bad, by just wrong answers, right? So continuity is a big deal. And mathematicians are a little uptight. I'll grant that, right? But still, it's a big deal. Reminder, well, let me say it this way. I'm going to define continuity for multivariable functions in a way that's very reminiscent of how continuity is defined for single variable functions. We're going to say that function's continuous at a point if and only if 3 requirements. The function has to be defined. The limit as you approach that input value has to exist. And those 2 things have to equal. Okay, so the value and the limit have to both exist, and those two things that exist also have to be the same thing. Okay, so I hope that looks familiar. Another way to say these three conditions, by the way, in some sense, the first two are sort of implied by the third, right? You can't have two things equal if either one of them fails to exist. Right? Just a point of sort of formality: does not exist and does not exist are not equal. Right? That doesn't make any sense. Okay, so you can look at this then and say, hey, on the one hand, maybe this is a definition of some abstract concept called continuity, but isn't this also kind of then a formula for computing limits? If I want to compute a limit, isn't this telling me that I can compute the limit with that formula? Don't I simply have to take the value that I'm approaching and plug it in to there? And wouldn't that then, doesn't this say that computes limits for me, right? And it's, that's the dream. Right? Wouldn't it be nice if you could just compute limits like that? And again, you can't just do that. A little too good to be true. Right? And the problem is ultimately one of what we call circularity. Right? You can't just say, oh, I'm going to compute a limit using continuity, because then you have to prove that the function's continuous, and you'd have to prove the function's continuous by computing the limit. And circularity is bad. Right? So it just doesn't hold any water. It doesn't make sense. Unless you already know, and here's the beautiful part about it, unless you already know for other reasons, if somehow externally you know that a function's continuous, let's pretend. If you happen to know a function's continuous, then you can totally use this formula and use the continuity to compute the limit. So the big question is, how do you know when certain functions are continuous? And good news answer to that is we get to inherit work done by previous mathematicians. Right? Previous mathematicians have proved that huge categories of functions are all continuous. Right? So all polynomials, they're all continuous. Isn't that nice? You don't have to prove that polynomials are continuous. You get to, doff the cap to, thank you predecessors and just cite that polynomials are continuous. Likewise, exponentials are continuous. And the list goes on. We do have to be a little bit careful. These other functions are continuous where they're defined. Obviously, trig functions are not continuous everywhere. Like tangent has got a great big gaping discontinuity, at which point it is also undefined. Right? So these are not all continuous, but they're all continuous where they're defined. Okay. Furthermore, if you have a sum of two known continuous functions, like maybe a polynomial plus a trig function, that's also continuous where defined. Likewise, products and quotients, blah, blah, blah. There's all sorts of, almost any way that you can think of to combine continuous functions results in a continuous function. So, nice example. Suppose you need to compute that limit, and this looks like a horrifying, intractable nightmare of a question. Right? Oh my gosh, look, there's tangents and exponentials and logs, and oh, yikes, oh, what a scary looking thing, right? But here we go. Here I have a product of two known continuous functions, so this term is continuous. Here I have a composition of two known continuous functions, right? Multiplying by pi over 3 is a polynomial. That's continuous. Tangent is continuous where it's defined. We'll come back and worry about that in a moment. This is a composition of two continuous functions and therefore continuous. Et cetera, et cetera. Everything in sight is continuous where defined. We're looking at a ratio, a quotient of two continuous functions, therefore continuous. All we have to do then is check that this monster is defined at this point. So just take that point, plug it in, note that everything in sight is defined at that value. Now, I recognize that at other values, tangent's not defined. At other values, log is not defined. Okay, sure, yeah. But I don't care. We're not going anywhere near those places. At the point 3, 1, everything in sight is perfectly well defined. Therefore, everything in sight is perfectly continuous. Because it's continuous, I can just do the plug-in method, and therefore our answer is this. End of game. And it's that easy. When it works, that's very nice. So that this does finish the section on limits for us. I do want to make a real quick comment before we wrap it up, and that is strategy. How do you go about deciding which of these various methods that you should use? Should I be checking different paths? Should I be hoping for continuity? Should I be doing polar coordinates? There's not an algorithmic answer to that question. You can't assume your conclusion and know what the answer is. Should you try to prove it exists, or should you try to prove it doesn't exist? If it exists, you should try to prove it exists. Right? If it exists, don't try to prove it doesn't exist. That's a loser, right? So strategically then, try what's most obvious. I think the continuity thing is always the first thing to look at, because it's really easy to check. Just look at where you're approaching. Plug in. See if everything in sight is defined. If it is, continuity, 100%. Next, give it a glance to try the polar method. Right? Look at that as a possibility. The things to check there are, make sure that you're approaching the origin. Right? And then also look for opportunities where polar coordinates will make things simplify really nicely. Like if you see x squared plus y squared in your denominator, that's a big win for this specific problem. Likewise, it was a big win for this specific problem. So look for conveniences that polar coordinates might afford. If neither of those applies, if your function's not continuous, most of them aren't, by the way, right? This is not continuous. Got a 0 in the denominator. It's just not defined at the origin. If polar coordinates isn't going to help, this polar coordinates, what would you do with polar coordinates here? The 7th power. I don't know what to do with cosine to the 7th. That's weird, right? Then probably start trying paths. Okay, y'all have a good weekend. See you later.
Thank you.